Hello everyone, I'm Chang from Institute of Computing Technology. Today I'm excited to present our work, Poby SmartNIC-accelerated image provisioning for Coldstart in cloud. Coldstart problem has long been a fundamental challenge in cloud platforms, which often incurs latency that is orders of magnitude higher than the actual request execution time, which significantly degrading user experience. Service computing further exacerbates the demand for ultra-low latency and elastic scaling, making Coldstart an even more pressing issue. Let's now examine two typical service models in service platform. First, when a user request arrives and if there is no available service instance, the platform triggers the slow Coldstart bars. In this part, the request must go through several stages before it can be served, which includes image download, extractor, container boot, and application boot. After the request is served, given the temporal locality of user request, the platform usually retains the application instance for a short period, so that the subsequent request can be served faster. After that, the follow-up request arrives during the retention window, will trigger the faster warm start bars, achieving a much faster response. When looking back at the entire response process of service requests, we find that the fast warm start bars is also built on top of the slow cold start bars. And image provisioning is essential for creating service instance, which is highly susceptible to the network conditions and the resource contentions. The image provisioning includes download and extraction, with the extraction further divided into the decompressed and unpack. Based on our analysis, we present our first key observation that image provisioning is the most time-consuming steps of Coldstart. This observation is also supported by a 15-day trace from Alibaba's function computing platform, which includes over 700,000 Coldstart requests, and more than 57% of these Coldstarts lasted over 45 seconds, and for over half of these cases, image provisioning accounts for more than 72% of the total time. Some researchers recognized this problem and attempted to bypass Coldstart by storing container snapshots in the memory or external storage, and then recovering from them for faster response. However, proactively catching such snapshots introduces significant overhead, and maintaining them in a distributed environment is quite challenging. Moreover, this method requires applications to be stateless. For example, if an instance retains a timestamp before the snapshot is generated and continues to use that timestamp after recovery in the future, this may lead to incorrect timing or even crash. Another line of work tried to avoid Coldstart by keeping applications always running. However, this leads to continuous resource consumption as well as violating the pay-as-you-go principle of service. Then some work attempts to predict the arrivals of requests to reduce the overhead of keeping instances alive. But such predictions are often inaccurate and costly. For newly deployed service, it is even more powerless. In summary, these two avoidance-based strategies impose the unrealistic demands of pre-profile. Specifically, warm start requires the accurate prediction of all request arrivals, while faster recovery depends on proactively catching all containers snapshots. These requirements are difficult to fulfill in the real-world systems. This leads to our second key observation: Coldstart from image provisioning is inevitable. First, catching all container images is not cost-effective. For example, CodeCrunch, a state-of-the-art warm start system, consumes up to 90 terabytes of memory to achieve just 80% warm start rate. Second, accurately request prediction is inherently difficult and requiring significant data storage and training cost for predicting models. There are also some efforts to try to directly accelerate the Coldstart itself by speeding up image download, such as using distributed image caching. However, due to the large number of images managed by the cloud platforms, caching such multiple image copies in distributed system introduced a prohibitive overhead. Other works proposed a new image format to enable on-demand loading, but these are often incompatible with existing systems and required significant engineering effort to large-scale applications. Importantly, these works tend to overlook the other critical steps beyond download. Hence, our third key observation is recent efforts ignore the image extraction process. Our experiments show that extraction accounts for over 68% of image processing time, making it the performance bottleneck. Furthermore, extraction is resource-intensive task. In our experiments, Redis experienced up to 110 times increase in tail latency when co-located with containers or containerd or iSulad during the Coldstart. To summarize, cloud platforms face two major dilemmas. Serverless computing exacerbates the Coldstart challenges, and the existing strategies fail to effectively address these problems. Therefore, we propose to directly accelerate the entire Coldstart process and completely solve this problem. Next, I will walk through the overall design of our design. The emergency of SmartNIC offers a promising new approach to tackle the Coldstart problem, which enables network-wide collaborative Coldstart offloading. As widely deployed network device in the modern data centers, SmartNICs are equipped with general-purpose SoCs and domain-specific hardware accelerators. This enables SmartNICs to offload computing tasks, and the SmartNICs are connected to the host server PCIe switches, and they offers up to 400 gigabits per second of low-latency RDMA network, making it feasible to faster transfer data across the clusters. However, putting this idea into practice still facing many challenges. The first challenge is the offloading dilemma. On the one hand, the ARM core on the SmartNIC have limited computing power and struggle with computing-intensive tasks like extraction. On the other hand, performing extraction on the NIC triggers massive small files transformed to the host, which consumes a lot of PCIe bandwidth. Thus, simply offloading the entire Coldstart process to a SmartNIC is inefficient. The second challenge is serial execution. Traditional Coldstart workflow follows the store and forward model, where each operation must wait for the previous ones to complete. Besides, offloading Coldstart to the SmartNIC adds additional operations as well as delays due to the cross-device data transmission. Since the store and forwarding workflow result in significant waiting delays. The third challenge is the centralized image registry. The traditional image download process is registry-centric. Even with RDMA, the centralized registry struggles to handle request bursts. According to our experiments, when the number of concurrent requests increased to 8, the image download times increased 6 times and 10 times for RDMA and TCP. The centralized image registry became a bottleneck during the Coldstart burst. To address these challenges, we first proposed disaggregated architectures or orchestrating the resource across the entire cluster to accelerate image processing. We began by leveraging the hardware accelerators on SmartNICs for decompressing. Our experiment shows that BlueField 2 achieves over 6 times better decompressing performance than the host CPU. To this end, we first decouple image extraction into decompressing and unpacking and leverage hardware accelerators to speed up the decompressing. Next, we restructure the Coldstart workflow by deferring the unpack steps to the host side. The new execution order avoids the transforming Nabrix files to NIC from NIC to the host after unpacking, significantly reduce the data transform overhead. As illustrated in the hardware architecture diagram, our redesigned workflow requires only one single cross-device data transform and avoid overloading the on-NIC SoC with unpack operations. Finally, we leverage SmartNICs high bandwidth RDMA capabilities to further discreting the decompressing to remote node. This leaves nodes only equipped with RDMA NIC to participate in our systems and effectively alleviates the local resource contentions. Our second design is the pipeline-based data-driven workflow to overcome the delays caused by serial execution. In an ideal case, pipelines can fully exploit the hardware parallelisms. However, in practice, partitioning the pipelines efficiently is challenging. A straightforward idea is to partition by the image layers. However, as the number of layers is limited, this coarse-grained approach unutilized the hardware and introduced the idle bubbles. Another idea is to divide the pipeline using fixed time cycle, similar to the hardware designs. However, since different hardware components have varying processing capabilities, hardware with high processing performance will remain idle during each cycle, leading to the intra-cycle bubbles. A third approach is to divide the image into fixed-size blocks. However, blocks differ in content as well as processing complexity. For example, highly compressed blocks takes long to decompress. This results in the inter-block bubbles to wet blocks with long processing time. To address above issues, we proposed the block-based redundant pipelines. We use the block-based pipelines to mitigate idle and intra-cycle bubbles and employs redundant hardware to absorb inter-bubble variations, and this achieves efficient pipelines. Moreover, we propose to change the control-driven pipelines to data-driven to alleviate the problems of control information exploding. As shown in this figure, the pipeline driven by control flow requires the controller to interact with each component to coordinate the pipelines. The block-based pipeline division requires the controller to coordinate these operations for each block with all components, which lead to the control information explosion. Then we embed the block index and the block schedules in each block to enable self-driven data flow. Block index specifies the position of a block in the layer and the images, and the block schedules indicate whether the block is decompressed on remote node or not. With this, each pipeline stage can automatically process and forwarding blocks without centralized coordination. Our third design is a distributed image download. We further proposed a best effort distributed download to minimize the overhead of distributed caching images. Specifically, only download images from nodes that happened to contain the required images without proactively cache. This workflow is shown in this figure. This figure summarized our system's 3 core designs. For more details, please refer to our paper. For the evaluation, we implemented a prototype of Poby on BlueField 2 and used Container D and iSulad D as our industrial baselines. We also compared against the 2 state-of-the-art systems. Uber's P2P best image system, Kraken, and the second is Alibaba's provisioning accelerator, FastNet. As for the workload images, we selected 12 representative images from DataBench, OpenWhisk, and Function Bench. Our performance evaluation shows that Poby achieves an average speed up of 11.5 times over containerd and 7.1 times over iSulad across all workloads. We also detailed the contribution of our designs to performance improvement, where effectively utilization of the hardware only introduced the Coldstart latency by 20%, while pipeline designs further reduced the latency by 34%. We also compared the concurrency and the scalability with the SOTA-Works. Poby is 4.8 times faster than the SOTA-Works at 8 concurrency, and it achieves comparable scalability to the SOTAs with nearly zero overhead. In addition, we also evaluated how Poby can reduce the resource usage on the host side. It's that Poby offloads the 55.3 of the host side user mode CPU usage to the SmartNIC and reduce 87% of CPU usage times. To conclude, we identify the key observation that Coldstart from image provisioning is inevitable, and SmartNIC can help fundamentally resolve the overlooked issue. Based on this insight, we designed 3 core mechanisms, and the prototype system achieved a 30.2 times performance improvements over the industrial baselines. That concludes my presentation. Thank you for listening. Any question?